Welcome. In this part, we will discuss about the block diagram and also the important components of numerical list. Now, this is a picture which has been taken from the textbook Python Grade Bytes. This is the block diagram of a numerical array. See, first of all, this is your power system where you will be having your transmission lines, alternators, transformers, etc. So this is a vast system. From here, I will be measuring the components which I wish to monitor. So there can be voltage or currents, or there may be any other quantities also. So most of the times, the voltage and currents at different parts of your power system, they will be measured. These are basically analog signals. So they will be measured here. So this kilovolts or kiloamperes of current, they will be, first of all, they will be scaled down to some reasonable values of 1 ampere to 5 amperes or 10 volts to 100 volts. So these kilo or mega values, they will be transferred or scaled down to these values with appropriate CTs and PTs. So once these are being scaled down and measured, so the data may consist of some sort of higher frequencies of components also, which may damage this entire equipment. So what I will do is nothing but I will use anti-aliasing filters. These are analog filters itself. So the data whichever is acquired from the CTs and PTs, it is being processed in order to eliminate the higher order frequencies. Once it is done, then I will move on to sample and hold circuits. The sample and hold circuits along with the multiplexer, because I will be getting too much amount of data, right? So let us suppose if I take at least one bus, it may consist of so many number of feeders, right? So all this data may be coming here. So this sample and hold circuits and multiplexer will help me in selection of that particular data, which data again I am supposed to process. So that job will be done with the help of sample commands and channel commands. So here multiple channels will be there, right? So multiple data will be coming from multiple channels. So out of that, which channel I am supposed to select? Let us suppose there can be V1, V2, V3, I1, I2, I3, like that. Multiple channels will be there. Which channel I am supposed to do? One at a time, right? So that will be selection of data will be done in the multiplexer. Once it is done, this is fed to your ADC. So that one selected data will be converted to digital data. Okay. So there will be some sort of processes you might have studied in your ADC. Start SOC, start of conversion, and again after the completion and conversion of data from analog to digital, again there will be a signal, end of conversion. Again it will be sent to your microprocessor, which means that the data is now completed. The conversion is completed. Once the data is converted to digital data, it is sent to your microprocessor, where you will be having some softwares and algorithms, and all this processing will be done. Once it is completely done, if you get a flag, which means if you find anything erroneous or anything not suitable or not satisfactory, then automatically what happens? You will give a signal, alarm, such that some measures are to be taken in the power system. So most of the times you give the trip signal to your relay, to your circuit breaker. So that job will be done by your microprocessor. So again this signal will be sent to your circuit breakers here. Circuit breakers will trip your power system. This is the concept. A simple block diagram of numerical array. So this microprocessor part we have already seen in digital array. So there won't be what will be there inside it. Nothing will be there inside it. It is just a processor. And the selection of software, so many softwares are available in the market now. And the algorithms, how you are going to write the algorithms, because you are getting some digital data, right? So based upon the digital data, you must be able to identify what is the problem, right? So that job will be taken care of by the microprocessor. So apart from the microprocessor, what are the important components here? CTs and PTs, anti-aliasing filters, sample and hold circuits, multiplexers, ADC, isn't it? So these are the important components, physical components of your numerical inlet. So let's have a quick look on the different components. The first one is filters and the CTs and PTs, right? So what is the job of CTs and PTs? Current transformers and potential transformer. They scale down the original values to the required range. Normally, the original values will be in megavolts or kilovolts or mega amperes to kiloamperes. So this will be scaled down to 0 to 10 amperes at the max, or 0 to 100 to 250 volts. So this process is done by CTs and PTs. And the data whichever you are getting, it cannot be directly converted into digital form. It may have some sort of higher order frequency components. So you should eliminate them. So such job will be taken care by a low pass filter. So the signals, whatever the signals which are acquiring from CTs and PTs, they will be passed through a low pass filter, which is an analog filter. Once it is processed, then the lower order frequencies which are present in your system. But that one, because there is a concept called as sampling theorem, which I will discuss in the next class. So for successful implementation of sampling theorem, you should ensure that your signal must consist of lower order harmonic components only, not the higher order. So that's why I am using this low pass filter. Okay, I hope you have now understood why I am using this low pass filter. And after this filter, if you have carefully seen, the first part is CTs and PTs. The next one is the filters, analog filters, anti-aliasing filters. And next we do have sample and hold circuits. This is one of the important. That is a must in your numerical level. So what happens is your job is now to convert the analog signal to digital signal, right? So during this process, after analog filtering, the analog signal is sampled and held constant during the time the value is converted into digital form. Okay. Normally what happens is the range of frequencies that can be handled by this ADC converter, it will be very quite low. Particularly without the sample and hold circuit, the range of frequencies will be very, very low. The sample and hold circuits, it will improve the range of frequencies which ADC can process. So it is just like, let us suppose you do have this data. Right. So the sample and hold circuit, let us suppose you want to measure the samples here. Right. So what it measures this one here. And up to this point, this data will be maintained like this one. So instead of an increasing one, during this entire period, the data will be stored in this format. So it is just like this original signal, sinusoidal signal, is being converted into some sort of stepped waveform, like whatever you call it as. Right. This is the concept of your sample and hold circuits. So it picks the sample and holds it till your next sample is being taken. Okay, this is a simple thing. So now let's see what is this is a simple comparison of maximum allowable frequency. As I already told you that sample and hold circuit will improve the maximum allowable frequency. Now let's see how this actually works. This is a simple example, not there in your syllabus, but you should know as an electronics engineer. See, this is the maximum dV by dt which your system can withstand, right? So this dV by dt, whatever the thing which you have for your signal, see, this is dependent upon V full scale, your meter what it can record by 2 to the power of n. This is a empirical formula, where this time is nothing but the conversion time of your ADC. If you do have a sample and hold circuits, then this will be replaced by this. This is acquisition time of your sample and hold circuits, because the signals are acquisited by your sample and hold circuit rather than directly by your ADC. At the same time, see, F max, this is your F max. This is the time taken, right? So the maximum frequency which is allowed. Okay, this is 1 by 2 pi into 2 power n TAD convert. So the similar one for this one. Now normally what happens is, let us suppose if I want to convert my analog signal to a digital signal of, let us suppose, 16 bits. Normally you do have 16-bit, 32-bit, 64-bit processor. So let us take it as a 16-bit processor. So whatever the analog data, let us suppose it is recorded as 230 sine omega t. This is your signal. I want to convert it into a digital signal. So these values, what are the values which are varying continuously, they should be converted into digital. Right? So I'll assume that there is an ADC of word length n is equal to 16 bits. So if I place here n is equal to 16, normally for A to D conversion by a converter, normally it takes 10 microseconds, the conversion time. But whereas if you do have a sample and hold circuit, the acquisition time of sample and hold circuit is very, very low. It will be of the order of 10 to the power of minus 9 seconds. So whereas for an ADC converter, it will be of the order of 10 to the power of minus 5, minus 6 seconds. See the biggest difference. This is an approximation which I have taken. So if you substitute this one, see the maximum allowable frequency here, if you get it is only 0.24 Hz. But whereas here you will get 9.7 kHz. This is the maximum allowable frequency with and without sample and hold circuit for your analog digital converter. So you can easily say that without sample and hold circuits, you can handle only extremely low frequencies. But with sample and hold circuit, you can handle much higher frequencies also. Now, having completed this sample and hold circuit, now you have understood why these sample and hold circuits are important for you. The next component you do have is ADC. Once your circuit is sampled and held, then it will be passed on to your ADC. Right? There will be a multiplexer also in between. The multiplexer basically selects the channel. So once it is selected, it will be passed on to your ADC. So this ADC works under the control of a microprocessor. There will be two commands. One is startup conversion, the other one is the end of conversion. Once you receive the signal startup conversion from your microprocessor, then it will start converting into signal. And once it is completed, it will give a signal of end of conversion again to your microprocessor. So ADC will give the signal and microprocessor acknowledges it. Once it is done, the data is now passed on. So this ADC converts your analog signal into your digital signal. So how many bits? It depends upon the microprocessor. It can be minimum of 4 bits to now 32-bit, 64-bit processors are also there. The wider the output of the ADCs, the greater will be the resolution. Okay, but too much amount of bits if you use, the system will become complex. So there is a limitation on that one also. So once you process the data, now the question is your microprocessor is taking the data now, right? Now it is to be stored somewhere, right? So that's why you will be having memory units also in your numerical list. One such memory is random access memory, or what you call it as a RAM. So whatever the digital values which you are getting from your ADC converter, they will be directly stored in the RAM. Okay, and this data, whatever the data which is stored in the RAM, that will be processed by your relay software. And the relay software will be having an algorithm also, which you have already written. So based upon this software and the corresponding algorithm, the data which you are saving in RAM, that will be processed here. And once you feel that it is not satisfactory, then automatically what happens? The microprocessor issues the trip signal on one of the bits of its output ports. You might be seeing this flag register above things, right? So it gives a signal. Then it is processed so that it is compatible with your trip coil of your CPU. Now the microprocessor can also be used to communicate with other relays also, which are in its jurisdiction or which are near to it. Or it can be used to directly communicate with some sort of supervisory computer, a central computer. Okay, and whatever the memory, it's now let us discuss confine ourselves to memory now, not communication. So in memory you will be having RAM, which temporarily holds the data, whatever the converted data is there, it holds that and it processes it. ROM, it consists of the software and the algorithm. And next there will be the settings, etc., 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 right? So that also will be there in your So it's not about the software or algorithm, the relay settings also will be there. So everything will be there, right? So all these things, they will be stored in the relay in different parts of here. So RAM will be there, ROM will be there, EPROM will be there. This is, see, the relaying program or the relay software which resides in the EPROM can only be upgraded or modified by authorized personnel. Sorry, here. Software algorithm will be stored in EPROM. In ROM, settings will be saved because the settings will not be changed all the time. Okay. So new functions, whatever the functions, if you want to change the functions and functionalities, that you can change in your memory. So you can upgrade your software, just like your mobile, you are upgrading your mobile, you can upgrade your software and get some new features also. Okay. So apart from this, the other components. Normally what happens is whenever it is not in use, the numerical relay can be made to run a program which periodically performs a self-diagnostic test and issues an alarm signal if any discrepancy is noticed. And there can be this type of watchdog timer also, which generally issues an alarm that the microprocessor does not reset it periodically. So it is just like for every some amount of time, period of time, it will be automatically resetting this. And that resetting time also will be some sort of few milliseconds. If it is not able to reset it immediately, then automatically it gives an alarm like your microprocessor is not working properly. So this will improve the confidence of the user, and also it improves the reliability of the relay. Okay. So hope you have now understood what are the different components in your numerical relay. And the conclusion is, numerical relay is just like an electronic device which is used in power systems to detect and respond to abnormal conditions. They have very good advantage when compared to the earlier generation relays. They have greater accuracy, they can operate very fastly, and the biggest thing is that they can communicate with other devices in the power systems satisfactorily. And they have this advanced technologies like self-testing, and they can log the entire data. Event logging is there. So all these things, they make numerical relay very advantageous. So that's fine. The modern power systems, basically they are employing numerical relays. So in the next lecture we will see, in the next lecture we will discuss about the advanced features of numerical relay. So that's it for today. Thank you. I hope that now you are able to describe the components